Problem number 56. Which among the following is a good quantum number for the Dirac-Hamiltonian for a free electron? We know the helicity, which is defined as the projection of the spin operator along the momentum, commutes with the Dirac-Hamiltonian for a free electron. So option C would be the correct answer. Problem 57. Consider a particle moving in one dimension under the influence of a parity even potential function v of x. Let psi be a normalized state where alpha and beta are two real constant coefficients, and psi naught and psi 1 are respectively the ground and first excited state of the system. The expectation value of the position operator x in the state psi is given by. So we know the ground state is even and the first excited state is odd. So let us now calculate the expectation value of x in psi. So this is equal to alpha psi naught plus beta psi 1 x alpha psi naught plus beta psi 1. So this is even function, this is odd function, this is even function, this is odd function. So the term like psi naught x psi naught would be 0 because this is a odd function. Let us figure out the remaining terms, which is alpha beta psi naught x psi 1 plus alpha beta psi 1 x psi naught. So option C is the correct answer. Problem number 58. Two particles of mass m each are subjected to a potential this. If a interaction potential of this form is switched on, the shift in the ground state energy to the first order in V naught is. We recall that the ground state energy of a particle under the harmonic oscillator potential is given by m omega by h bar to the power 1 by 4th e to the power minus m omega x square divided by 2h bar. Let us find the correction to the energy of the ground state, which is given by psi naught of x1 x2 phi interaction times psi naught x1 x2. This is equal to m omega by pi h bar, and we have an integral of dx1 and another integral of dx2, and e to the power minus m omega h bar times x1 squared plus x2 squared times this potential v naught x1 squared plus x2 squared times the delta function. Now we do the x2 integral, which makes x1 equal to x2. So x1 integral remains, and we have minus 2 m omega x squared divided by h bar. V naught can be taken outside, and we have 2x1 squared. So if you do this integral, you will find m omega pi h bar v naught times half times pi by square root of pi by 2 times h bar m omega times square root of h bar m omega. Now we simplify things, so h bar cancels out, m omega cancels out, so we have phi naught square root of h bar by 8 m omega pi. Let us go back to the options. I do not see any option that is matching with the result we obtained, so I leave it to you to figure out what the correct answer would be. Problem 59. Let J be the angular momentum operator and A and B be two constant vectors. Then the commutator this is equal to, so we write the commutator as AI Bj commutation relation of Ji and Jj. We know this thing is equal to I h bar epsilon I j k j k. So we have I h bar epsilon I j k ai bj j k, and this is equal to A cross B dotted with J. So option A is the correct answer. Problem 60. Consider the Hamiltonian of a system this where epsilon naught is a constant and h1 and h2 are given by this 2 cross 2 matrix. The symbol denotes the direct product. Which of the following statements is correct? First, we find the eigenvalues of this Hamiltonian, and these are easy to find. Let us assume that lambda 1 and lambda 2 are the eigenvalues. So, lambda 1 plus lambda 2 would be the trace of this matrix, which is 2, and the product of lambda 1 and lambda 2 would be the determinant of this matrix, which is 0. So from these two we can figure out lambda 1 could be 2 and lambda 2 is 0. The energy for this Hamiltonian would be E1 plus E2, where E1 corresponds to the space H1 and E2 corresponds to the space H2. So the ground state energy would be minus 2 epsilon naught minus 2 epsilon naught, which is minus 4 epsilon naught, and there exists only one state. So the ground state energy is minus 2 epsilon naught and it is non-degenerate. So option D is the correct answer.